In this video, we're going to look at rates of change and behavior of graphs. So in the warm-up here, I'm asking you some questions based on prior knowledge. So if you're a little shaky, that's okay, and we'll go over these in class. So I want you to read through them. I want you to think about what your answers could be if I call on you, or if you're willing to volunteer. So in your own words, what would you say a slope of a line is? If I asked you to find the equation of a line through 2 points, what is the process you would do to get there? What is the relationship among graphs of lines with equations of y equals mx plus 2, where m is the real number? And what is the relationship among graphs of lines with the equation y is equal to negative 0.5x plus b, where b is any real number? So we've talked about slopes in previous math courses. We want to think about slopes of lines as being rates of change. So if we take any 2 points on a line, the ratio of the change in y with respect to x, the change in x, as the line goes through one point to the next is, we want to think of this as like the slope, the change in y over the change in x. You might see the notation delta y over delta x. The delta, or that triangle shape, means delta or change, so change in y over change in x. One of the ways that we can represent it algebraically is y2 minus y1 over x2 minus x1, and it doesn't matter if you did y1 minus y2 as long as you did x1 minus x2. So the order in which you do this doesn't matter as long as you're consistent. So if you want to do y1 minus y2 over x1 minus x2, totally fine. If you were in the land of functions, you can write it as f of x2 minus f of x1, because remember, f of x2 is the same thing as y1. If it's a function, you're going to replace it notationally with y1, y2. So f of x2 is y2, f of x1 is y1, and of course, x2 minus x1. If we don't have a line, and we're talking about this average rate of change, then it is not a slope of the function. If we're talking about a function, it is the slope of the secant line of the function. And what does that mean? Well, let's take a look at this first example here, and it says, what is the average rate of change for this given function or the graph? This is not linear because we have x squared. If I were to draw a quick sketch of this graph, it would look something like this. It would have a negative 9 as an intercept, and there's a 2 in front of the x squared. Parent function is, of course, the quadratic or x squared, the squared function, and it has a 2, so it has a vertical stretch, and you're like, what? Don't worry about it. I'm not going to draw this to scale because this is going to be difficult for me to draw to scale simply because I need to talk about this. Now, assume we put in 4 into my function. So I'm going to put in 4. G of 4 is equal to 2, 4 squared minus 9. Well, 4 squared is 16. 2 times 16 is 32. Minus 9 is 23. So here is that first ordered pair, 4, 23. B is any arbitrary number. So suppose I want B to be, say, 7. Okay, so let's expand this out. And here's 7. So it would, let me expand that out. This is y and this is x. So 7 would be somewhere right here, right? And even though it kind of looks like a straight line between these two, when we're finding the slope of the secant, poorly drawn, when we're finding the slope of the secant, we're finding that. So when we want the average rate of change, we're finding the slope of the secant. We're finding the line that goes through those two ordered pairs. It is not necessarily the function. If the function is linear, then the average rate of change is the slope of the line. This is not linear. So I just wanted to show you what we're doing and why we call it the average rate of change. And it's not necessarily the slope. We won't say the average rate of change is the slope. It's the slope of the secant. It's the slope of the line if the function is linear. Okay, so how do we do this? Well, we're gonna do the average rate of change by using this equation up here, right here. It says this average rate of change is going to be f of 2. Well, this is 2. This is x2. So I have g of b. This is the same thing as f of x sub 2, which is 2b squared minus 9. Okay. That means, and then my g of 4, which is f of x sub 1, which is going to be 2 multiplied by 4 squared minus 9, which we know is 23. So using that formula, f of x sub 2 minus f of x sub 1 all over x sub 2 minus x sub 1, this is going to be the order, this is going to be the average rate of change. It'll be 2b squared minus 9 minus 23. Now, this represents f of x sub 2, and this represents f of x sub 1. All over x sub 2, which is b, minus x sub 1, which is 4. So this is going to be 2b squared minus, well, this is 32 over b minus 4. Well, this factors out, so I can factor out of the numerator 2, leaving me b squared minus 16 all over b minus 4. This continues to factor. The numerator is the difference of squares, so b minus 4, b plus 4, all over b minus 4. You've seen in previous videos that this then cancels. So my answer, my average rate of change is 2 multiplied by b plus 4. So that's my answer. And you have to go through all of that process to simplify for the answer. So before you ask, yeah, you have to simplify. Now this one's a little bit more sticky wicket, as my husband would say, a sticky wicket, because he's British. So let's do this. Okay, so I'm going to find my f of x sub 2, which is going to be b of 1 plus h, which is 1 over 1 plus h plus 3. My f of x sub 1, which is going to be b of 1, which is going to be 1 over 1 plus 3, which is 1/4. This reduces to 1 over h plus 4. That's just going to make it a little bit easier, somewhat easier. Now, f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. This is going to be equal to, I'm going to have 1 over h plus 4 minus 1 over 4 all over 1 plus h minus 1. So in the denominator, that's easy. We just get h. In the numerator, I have these two fractions. Option A is I make a single fraction in the numerator and then multiply by the reciprocal of the denominator fraction to simplify. Option B is I multiply everything by my lowest common denominator. So I'm going to multiply the numerator and denominator by 4 multiplied by h plus 4 because that is the common denominator of those two fractions. And whatever I multiply the numerator to, I have to multiply the denominator as well. When I do this multiplication and I distribute this through, you can see the h plus 4 will cancel, leaving me just 4. And then minus when I multiply it here, the 4's will cancel, leaving me minus h plus 4. In the denominator, I'm going to get 4h, h plus 4. In the numerator, this is going to cancel into 4 minus h plus becomes a minus 4, all over 4h, h plus 4. In the numerator, my 4's cancel, so I get negative h over 4h, h plus 4. h's will cancel, so I get negative 1 over 4, h plus 4. And that's my final answer. Excuse me. Algebraically, it can be a little cumbersome, especially if we're doing simplification. The average rate of change on a graph is awesome. You're like, woo, awesome. So I want to know, and this is where you definitely see the secant line, is I want to know what's happening from 1 to 4. So here is the ordered pair 1, 5. When I put in 4, it looks about 3.5 is coming out, and I can just simply count. This way is my change in y, or excuse me, a change in x. And this way is my change in y So my change in y and over my change in x, my change in y is going down, so it's negative 1.5. And then my change in x from 1 to 4 is 3. Now here's the thing. We do not leave decimals inside of fractions. So I'm going to multiply the numerator and denominator by 10 because I have 1 decimal. So I have 15 over 30, which reduces down into 1/2. And that is my average rate of change. Oh, and here you can clearly see there is my secant. We do m of secant is equal to 1/2. Kind of cool. All right, now let's talk about what it means to be increasing, decreasing, and constant functions. The definition for increasing is a function is increasing if for every a, which is on the left side of b, f of a is less than f of b. So the outputs, if a is on the left side of b, a is less than b. The output when I evaluated at a is less than the output when I evaluated at b. We call this increasing on that interval. Notice I don't include the endpoints. Decreasing on the interval is if a is less than b, a is on the left of b, and the output of a is larger than the output of b, then we say it's decreasing on that interval. Lastly, we have a constant. So if a is less than b, and for all a's, everything between a and b, if the outputs are the same, then we say it's constant. If, this is important, if the average rate of change is positive on that interval that we're looking at, all of the average rates of change are positive on the interval, then the graph is increasing from left to right. If the average rate of change for the entire interval is negative, the graph is decreasing from left to right. If the average rate of change for all possible choices in that interval is 0, then the graph is constant. Here's an example. So in this interval between -infinity to -2, I am increasing. I'm going up the hill. So if I asked to where I was increasing, I'd note it as increasing as from -infinity to the x part, which is -2. So right here is the x part in which it changes. So that's increasing. The next time I'm increasing is right here at 2. So 2 to infinity. So I'm uniting this with 2 to infinity. The places in which I'm decreasing as intervals, I'm looking for the x values, not the y values. The x values of which I am decreasing is between -2 and 2. And you're thinking, why am I not including these points? Well, at this point, and this particular author of this book, do not include those turning points, that moment I turn from increasing to decreasing. We're going to call those extrema. We don't include those when we are talking about intervals of increasing and decreasing. We do not include these turning points, the points in which I go from increasing and decreasing. Now, some books will, this book doesn't. I don't for this level of math. And that leads us into extrema. The extrema is where we're looking at these turning points. And these turning points are either going to be local maxima or local minima, or they could be absolute. So what is the difference? What does it mean? Well, a local minima is the lowest point on some given interval. The local maxima is the highest point, or that turning point, the point at which I turn from increasing to decreasing or decreasing to increasing. Is that moment where I turn from increasing to decreasing or decreasing to increasing. And we call those local maxima or local minima. Depends if it's a high point or low point. We have absolutes. In Calculus 1, we will talk about absolutes being endpoints. Absolutes can happen at endpoints. The book that we use, OpenStax, the author does not include the endpoints as locals. So we will follow that. So if we have any endpoints, we will not include those in any locals. Absolutes could be the endpoints. What I mean, like, what the heck is she talking about endpoints? I'll show you. But let's go back to this example, this graph up here. If I wanted to know where is my local maxima or minima, if any, it is where it happens and what it is. I don't give it as an ordered pair. Don't give this stuff as an ordered pair because it makes no sense. if it's an application especially. So I would say at x is -2, the local, when x is -2, the local max is 16. And I'm not going to give it as an ordered pair. And then I'd say at x is equal to 2, the local min, or minima, if you want to write it all the way out, is -16. Because this goes down forever and it goes up forever, it has no absolute. There's no place on this graph that it has the highest or the lowest point. Notice maximas and minimas are almost never wrote as ordered pairs, and I will be very explicit. Do not write these as ordered pairs. So you'll know on any assessment not to write them as ordered pairs unless I tell you you can. If I don't tell you you can, you have to write it as at this x value, this is the absolute, this is the local, this is maxima, this is minima. And notice it's broke apart in two places, the place it happens for the x and what it is, which is the y. So remember, the endpoints of the intervals of increasing and decreasing, which are the extrema or the maxima and minima values, are not included in the interval of increasing and decreasing. Here is absolute. Absolute will happen in which we have the endpoints. So we talked about endpoints. We're like, what? So let's take a look at this. Right here, this is the lowest point, and it is an endpoint, and there's a dot, so that is included. So the absolute min of -3 happens at x is equal to -5. Now notice, I'm still giving the information, but I'm not necessarily writing it the exact same way. So it's not important to write it the exact same way as I do it, but you do have to bust it apart as what is it? You're telling me the y value. What is that y value you're telling me? Is it an absolute? Is it a local? Is it a minima? Is it a maxima? And what the value is. And then I'm telling you where it happens. Now, this is an endpoint, and it's a low point. So it is neither an absolute, because it's not the lowest, and I don't include endpoints for my local. So that is neither absolute local or it's neither absolute or local minima, and it's definitely not a maxima. So the other part is where am I increasing? Well, my intervals of increasing are in the interval non-inclusive between -5 and 1. These are the x values. Oh, I guess it's -5 to 1. These are the x values that produce the uphill battle. The decreasing is the interval between, looks like 3 and 5. That's these. Between 3 and 5, I'm going downhill. The constant is in this region. So the constant, I am constant on the x values of 1 to 3. Now, why don't I have any other extrema? Well, let's look how we described the extrema. Right here it says, f has a local maximum at x equals b if there exists an interval from, and it's an open interval. See how we have non-inclusive endpoints. A is non-inclusive, C is non-inclusive. This is not an ordered pair, this is an interval of numbers. If for every A, which is less than B, which is less than C, such that for any x in that interval between A and C, that output at f of x is less than the output of f of b. That is how we define a local maxima. So in other words, the largest output in that interval is going to be the interval in which we have b as the output. Another way you want to think about it is if I come in increasing and I leave decreasing, then at that point, I have a turning point, and that's the location of a maxima. Likewise, a local minima, f is equal to b, there exists an interval from A to C, in which A is less than B, which is less than C, that for any x in the interval A to C, f of x is greater than or equal to f of b. So in other words, f of b is the lowest output. So you're like, okay, well, why can't I, I don't understand, why can't I have an interval here that includes the point, a turning point, at 1, 3. It looks like 1, 3 is going on. Something's going on there. So let me erase this and let's talk about this. Suppose I have an interval that starts at 0 for x and ends at 2.5. So I start at 0 to 2.5. So here is f of a, and here is f of 2.5. Now, by my definition, this has to be, if I think that's the point in which I should have a maxima, that has to be the highest point. Now, the problem is that in this region right here, that isn't the highest point. There's an infinite number of numbers that produce that same output in that region. That's why I'm not going to include this point or for the same as that point, for the same reason. I'm not going to include those points. They are neither maxima or minima because it doesn't follow the definition. I know it's really confusing, but always go the definition if you're not really certain. Okay, so using that kind of logic, let's look at my next example. Well, right here, this is the highest point, and it is, and I get to include it, 1 because it has a dot, and 2 because it's an endpoint. It is the highest point, so we have an absolute. This is an absolute max of 4 at x is equal to 5. Right here, this is the lowest point in that region, and I come in decreasing and leave increasing. So we have a local max, or local min, of 1 at x is equal to 1. Again, have I wrote them differently several different times? Yeah. But the important is I tell you what it is. I'm classifying the extrema as absolute or local. I am classifying the extrema as a minima or a maxima. I'm telling you what the actual value of it is, and then also I'm telling you where it happens. So how you write that is up to you, just not as ordered pairs. So let's go and do the increasing. I am increasing in this region of x's, so I'm increasing between 1 and 3. I am decreasing in this region between -5 and 1. I am constant in the region between 3 and 5. Now, this point and this point, because they don't come increasing, leave decreasing, there's no way I can get an interval in which my definition of what it means to have a maxima and minima are going to uphold. And this endpoint is neither the highest nor the lowest point, so it is not an absolute. So I have two extreme. I have an absolute max. I have a local minima. I have other points that are not really all that interesting, but I do have intervals of increasing, decreasing, and constant. All right. From these graphs, we want to estimate the intervals in which the function is increasing or decreasing, find any max and minimas, and state if they're local or absolute. Now we make the assumption, unless otherwise stated, that we are going to go up forever, or in this case, go down forever. I want to know my intervals of increasing. Well, I am decreasing in this region. Remember, it's the x value, so I am decreasing between -infinity and the x value of 0. I am increasing in this region, so increasing between 0 to infinity. This is the lowest point that I can see on this graph, so I have an absolute min of, looks like multiples of 2, 3, it looks like 5, -5 at x is equal to 0. Okay, right here is the location of decreasing. So I am decreasing on this one between 0 and infinity. I am increasing here between -infinity and 0. And then I have an absolute. This is the highest point from what I can see. So I have an absolute max of 3 at x is equal to 0. Let's take a look at these. Now, these are a little bit more interesting. So I have some turning points. I have maxes and mins. I'm going to have to estimate, right? So paying attention to my grid marks, this is -1, this is +1. It looks like I am decreasing to about here. So my decreasing, paying attention to my intervals, looks like it's going to go from -infinity to maybe -0.6. And it looks like I'm decreasing right here. So it looks like I pick up a decreasing again about 0.3 and to, well, it looks like 1. So that's kind of nice. So there's my decreasing. I am increasing. I'm increasing in this region. So I can just look at my endpoints, and I have from -0.6 to 0.3. And then I start here and increase again. So from 1 to infinity. Right here is the lowest point. So let me do that in blue. And I'm going to say an absolute min of lowest point looks like it's about -1.5 at, well, x is equal to -0.6. And I know that because I am changing from decreasing to increasing, so I must have a minimum there, and it's the lowest point, so it's an absolute. Right here is a local max, because these are going up forever, of, it looks like -1.6 at x is equal to 0.3. And then right here, this is so sloppy. Here's my last one, and I'd say a local min of looks like about -1.9 at x is equal to 1. So that's that one. And again, I had to estimate because I didn't have some really nice grid marks to determine that. So let me go ahead and erase this, and then we'll do the second one here. And this time I'm going to go ahead and scroll in. Paying attention to my grid marks, this is -1, this is +1. In this region, I am increasing. So I'm increasing in here, and it looks like about right here I'm increasing. So I am increasing on the interval between -infinity, and it looks like about -0.6. And I pick up the increasing again. Notice how when I do increasing, decreasing regions, I start left and go right. The next time I am increasing looks like about 0.6 to infinity. That means this is my region of decreasing. And I can tell by these two endpoints, this interval is the location of decreasing, so -0.6 to 0.6. No constants. This is a local high spot, so I have a local max of, looks like about -1.6 at x is equal to -0.6. Here's a local low point. This is a local min of, looks like about -2.4 at x is equal to 0.6. All right, so here's an example. I will see this on the homework. I might see it on an assessment, maybe show up on a quiz, and I get all my information from the graph. So the backyard farmer wants to enclose a rectangular space for a new garden with her fenced backyard. She has purchased 80 feet of wire fencing to enclose 3 sides, and she will use a section of the backyard as the 4th side. Now here's the graph. What the heck is going on? I'm going to draw a quick little sketch. So here's what she's fencing. This is already given. So this is existing fence. So this side is x, this side is x, and this side is y. So I know x plus y, all of those sides have to equal 80. That's the perimeter. So 2x plus y is equal to 80. Now the other thing that's happening, if I want to find the area of this, then all I'd have to do is multiply the two sides. So the area And that's what I'm trying to maximize. The area would be x multiplied by y. Now look, we have two equations, two unknowns. Let's make this into one function. A of x is equal to, if we take this and solve for y, I've got y is equal to 80 minus 2x. Then I can replace this y with that value. So I have x 80 minus 2x. So that is what they're asking for right here. A of x is equal to x 80 minus 2x. Now, looking at the graph, I'm looking at the possible x values. Well, obviously, it would make no sense for this graph to go down forever, right? Because that would tell me, if I'm graphing the area, then that's going to tell me that my area is going to go negative. My outputs are the area. My inputs are the length of one of the sides. So, based on this graph, even though this function has no restrictions, within the application, it certainly does. The lowest length I could put in is close to 0. The largest length I can put in is close to 40. So this is my domain, non-inclusive of 0, non-inclusive of 40. Now, using the graph, determine the dimensions of the graph that maximizes the area. Right here is the information that I need. When x is equal to 20, the max is 800. This is why we don't do max and mins as ordered pairs. Where does it happen? What is it? Have we answered the question? Well, no, but we're getting closer. I know when x is equal to 20, that means that my one side of my dimension is 20. So I have 20, and what are my units here? Feet. So 20 feet. That's what x is equal to. So if x is equal to 20, I'm going to go right back over here. Notice this, and that's going to tell me what my y is. Well, my y is going to be 2 times 20, which is 40. So I have 40 feet, which is equal to y. And so here are my dimensions. And I was able to do it by my graph, which is looking at the maxima. All right, so when we are looking at the toolkit for increasing and decreasing, what I'd like you to do is I'd like you to open up your book and fill in this portion of it, because it's there in your book, and it's really nice to be able to use your book because it is a really good resource. I chose this book because it reads very well for both students and people who are teaching from it, and I want you to fill in this chart for all of your toolkit of functions. So notice there is all of these toolkit of functions, and so I want you to finish filling that in. And that's it for this video. And I want you to do this because I want you to go through and be comfortable with all of the toolkit of functions, and I want you to do this. Sure, you can copy and paste it, but don't. I want you to write it. There is studies that show if you write stuff down, you're more likely to remember it. So I am hoping that you have downloaded these notes and you are now filling in your notes based on this video. And that's it.